like that on both sides. But if I project that triangle up to it, that's the only part that actually contributes to the volume of this 3D space. Okay. Not part of the problem, it's just good to see what your, your 1/3 stands for. Okay. So far so good.
Is that the volume from the graph to the bottom of the paraboloid?
From the XY plane is your base, so this down here is our region R in the XY plane. Okay? And then if it's projected upward to using the paraboloid on the top, so that's the top of the solid, and that's the underlying space beneath it, this calculates the 3D volume of that, all that space.
Okay.
Yeah. With that triangular base, and you got a flat face here, you got a flat face there, you got a flat face on the other edge, and you have a curvature on the very, very top. That's defined by the paraboloid itself. Looks like some kind of fancy award, or a really good weapon in the game of Clue. You really damage Colonel Mustard with that really badly. Okay, should give you the same thing here. A handful of you evaluated both of them. Did anybody evaluate the other one? 1/3 also?
I did, but I got negative 1/3.
And that's a problem, because if it's described as a volume, it should be entirely positive. So your antiderivative for y first, well, let me work this later. If you want to see this, I'll double check it after class if you want to, but it should, just double check your work. It should give you a 1/3 in the answer. It should. All right. Maybe the only thing I can imagine is if you got the right number but the wrong sign, you may have reversed the order of plugging in your limits. You may have accidentally plugged in an x first and a 1 last. And if that's the case, you've reversed the fundamental theorem. And that would cause you to get the same number but the wrong signage. So, unique problem here. Evaluate the double integral for the function 8xy over the region bounded by these curves. The curves are y equals 4, y equals x squared for x less than 0, less than or equal to 0. Set up both orders of integration and determine one of them, choose one of them to do, just to get your value. I want you to do the graphing and set up one of the two orders, and I'll do the other one. Well, obviously I'll do both of them. But keep in mind, the function that's mentioned is, set up a double integral for this function. That's eventually going to be your integrand. It plays no role in the graph that you're making for your 2D region. Just double checking the other one real quick.
Yeah, it's the plus 1/3. Because
That's what it is.
so yeah, I've just on my right to the last, I've got 4x cubed over 3 minus x squared minus 1/3. So whatever. Sorry. Oh no, you're correct. I just missed it.
It's 4 terms. Because those are like terms.
Oh no, you know what you're doing?
What am I doing?
You did not divide your 4/3 by 4 because you have to integrate x cubed, right?
Plus 1/3.
And that gets you, eventually when you plug in one, it's 1/3 plus 1/3.
Duh, I didn't even integrate. Hell. So yeah, that's a third, that's a third, and that's 1/3 x to the 4th. Thank you, yes. Okay. Was that your mistake also, Matthew? I just completely forgot to integrate this critical
No,
number here.
I got 1/3 x
So
to the
when you plug in
4th
1,
minus-
a pair of those thirds cancel out.
I just got 1/3 x to the 4th minus 1/3 x to the 3rd minus x to the 3rd. I'll go back and get it in a minute.
It does give you the same answer, so, sorry, Frank did.
Got one too many minuses. Other than that.
Usually,
everything's wrong.
when you're choosing an order of integration, sometimes people just go on based on the way the functions are defined. Your only real, I guess, tricky function here is y equals x squared. Since it's already defined as y equals a function of x, a handful of people kind of train themselves to do the y direction first. That really lends itself to doing the y direction easiest first. So probably the easiest order to do first would be dy then dx. And alternately, we should be able to come up with dx dy. Who did the dy dx order? What'd you get for your y limits?
X squared to 4.
X squared to 4. And when you flatten it to the x-axis, what's left over?
Negative 2 to 0.
Negative 2 to 0, yes. And let me show you why. Because when you graph this region out, the region bounded by the curves y equals 4. Y equals 4 is a horizontal line. So we'll have y equals 4 right about here. Y equals x squared is that parabola we've been dealing with. But I don't need the full one because the last inequality there says you want the region bounded by those curves, which currently would just be that cup up to the line y equals 4. But if you cross it with this inequality, you only want x values that are less than 0, less than or equal to 0. So you technically start at the y-axis to the left, or you're only left of the y-axis. So the region that you're using for whatever order of integration you want to choose should be the left half of that parabolic space. Okay? And so yeah, because the way these are originally defined, the parabola is defined as y equals x squared, the horizontal line's at y equals 4. The intersection point here is at negative 2, 4. That'll come in handy when we flatten everything to the x-axis. So if you commit to doing the y direction first, you needed to have that picture. Going in the y direction through this space, the first thing you hit is y equals x squared. The last thing you would ever hit is y equals 4. So those are correct for the y limits. When this is flattened to the x-axis, all that's left there is from negative 2 to 0. So those are your correct dy and then dx limits. What about your dx dy limits? Going in the x direction first, what's your lower and upper limits on entrance and exits?
0 to x squared.
The square root of y.
Yeah.
Yeah, making a transition from going upward to leftward. If you enter this in the increasing x direction, okay, envision several different horizontal rays piercing into this space, into this 2D object. You're going to enter at this x boundary, but you have to redefine it as x equals something in terms of y, or x equals a constant. In this case, it's x equals
Negative.
negative root y. Yes, because you're dealing with the left half of this parabola, the place where x is negative. So x actually enters at negative root y, and then exits at 0. X equals 0, the y-axis. And then you flatten this to the y-axis, and all that's left is 0 to 4. Our integrand is not too terribly bad, but which one would you choose?
It's 2 0.
It's got 2 zeros, but it's got that messy square root. Oh my lord! Don't let the square roots intimidate you. I mean, I would probably say the use of zeros there trumps the fact that there's a square root in it. And keep in mind, when I integrate x, and I plug in these limits for x, x here will be squared after doing this antiderivative. And squaring a square root is going to work, very nicely. So yeah, I'd probably do this just because it has more zeros in it. So if I commit to doing that one, oops. 0 to 4 is my outer limits. Negative root y to 0 are my inner limits. 8xy is my integrand. So if I integrate with respect to x, going from inside out, you kind of have to, that's going to give me 4x squared y. I figure I can only do calculus correctly if I'm speaking it as I'm doing it. If I do it quietly by myself, I tend to make mistakes. So it's going to make Dave and Judy and Beth, well, Dave and Judy really pissed off that I started doing that.
Can I try that when I'm doing my tests?
Your testing center, that may not fly too well. They'll probably put you in a bubble. If you plug in 0 for the x, that wipes everything out. When you plug in negative root y for x, the negative and the root are going to go away. So you have 4y times y, you end up with a negative 4y squared. Okay? Then, do your outer order of integration. I want to integrate that with respect to y next. And so remember, I'll go back over here and plug my y limits in when I get done with this one. That's going to give me negative 4/3 y to the third power rule. You get a lot of power rule with these double integrals. And then when I plug 4 in for y, that's going to give me negative 4 to the fourth is 256 thirds minus 0. You get a negative answer. Is that puzzling? Have you ever had a single integral that gave you a negative answer? From Calc 2. You had some integration that gave you, negative answers, like, in the context of like a velocity problem. If you integrate your velocity and you get a negative displacement, that means you've moved more further, displaced more left than you have right. It's just, sign values, don't let them freak you out too bad. But look at the region that we're integrating over, the domain of our double integral, and then consider the outputs of this function. The function's outputs are generated by doing z equals 8 times x times y. Every output for this function on that domain is what sign?
Negative.
Either negative or 0. If you're on the boundary right here at the y-axis or at the origin, your output's going to be z equals 0. Every place that's properly inside the second quadrant, your x values are negative, your y values are positive, your outputs are generated by 8 times x times y. You have nothing but negative outputs except for the z equals 0 that's on the y-axis and the origin. So it's okay. You get negative answers sometimes. Don't let it flip you out. Not every double integral is tied in with the notion of volume. I guess if you wanted to think of that, this surface, since it lies entirely below the xy plane, it would look like here's the domain, the function lies below it. You're technically calculating that negative volume that goes from the xy plane down to what that surface looks like. If you want to tie it in with volume, you don't have to. It doesn't always have to be a volume context. But it's okay to get negative answers. And, feel free to double check the other order of integration. It has to give you the same answer, that negative 256 thirds. Yes, sir?
Is that going to be similar to if we integrate like a sine function that's going under the curve?
Yeah. Like in Calc 2, if your graph goes below the x-axis, some of your teachers may call that just a negative area because the function's below. So same idea here. If the function, if you analyze the outputs there, that function is entirely below the xy plane for all of its outputs. You have no help but to get a negative answer. So yeah, that's kind of like the same thing as when your sine wave dips below the x-axis, you get a negative area. That's kind of like a negative volume. Right? Let's see.
Why wouldn't they put absolute values on that?
Oh, I don't think, we actually brought that up in class, I think last week. If you wanted to find, I guess, the volume, you could take the absolute value of your answer. It would represent a 3D space, but it's below the xy plane, so it just looks weird when you graph it, because the top is your region R, and now the function is down below it, so it's kind of like an inverted version of that.
Okay.
So, but if you get a negative answer or even a positive answer, remember, it doesn't necessarily mean you're entirely negative or entirely positive. It just means the net result of adding up all those outputs for the double integral's value. In this case, you have more negative than positive, or in the positive case, you have more positive than negative outputs. It doesn't mean it always has to be entirely positive or entirely negative. This one is a bit of a twist because you've got two curves. One has y a function of x, and the other one has x being a function of y, which pops up every so often. You had to deal with that a few times with area between curves and volumes of revolution solids when you were in Calc 2. So same idea. Sometimes you may have to graph some sideways parabolas. Don't let it freak you out. You can always solve this for y. But remember, that's going to generate two different equations you'd have to graph in your calculator if you solve this for y, because you'd have a plus or minus square root to solve it with. So if I graph these, the region R here is just bounded by those curves. Nothing like y equals 1 or x equals 0 or x greater than 0 is mentioned. So apparently when I graph these out, I should see a proper bounded region. So, let's see. Y equals 2x is the same one we dealt with earlier. It's just a line through the origin with a slope of 2, so that one's pretty straightforward. X equals y squared minus 3. What would the graph of that look like?
So parabola,
A
sideways
parabola opening
parabola.
which way? Opening to the right. What's the effect of the minus 3 do to
It makes it go back. It goes to the right.
Left. Yeah, because notice if you actually found the x-intercept, so you plug in y equals 0, it should have an x-axis intercept. Instead of at the origin, the intercept would go to -3, right over here. So that -3 actually causes your sideways opening parabola to shift 3 clicks to the left in that case. So it's kind of like the reverse for functions. For transformations, that is. You're used to x minus something meaning right and x plus something meaning
I
left.
just had it backwards.
It kind of flips over here because you're reversing the dependency. You're making x depend on y versus y depend on x. So that's now a sideways opening parabola. And like I said, if you have to go to your calculator and graph this, it depends on you solving for y. You'd have to enter y equals the square root of x plus 3 as one entry, maybe like y1. And y2 would have to be the minus square root of x plus 3. And so those graphs, graphed in tandem, would produce that upper and lower half of the sideways parabola. Okay. So, what order of integration would you want to commit to here? X then y. Kai is right off the bat saying x then y. Does everybody agree with that?
Yeah.
Those who don't agree, I need you to see why that is the most practical order of integration to use here. Because if you decide to go in the x direction first, what you need to mentally envision is drawing like an infinite set of those horizontal rays. Am I always going to enter on the same boundary? No, look. If I go this way, am I always entering on the same equation?
Oh, yeah.
Keep in mind, that's the equation you need to use. Yeah. You're always entering on the equation x equals y squared minus 3. You're always going to exit on this equation, which is x equals half y over 2. You got to reverse the dependency depending on which order of integration you do first. So if I chose to do the y direction first, imagine drawing a set of vertical rays going in the y direction. Do I have consistent entrances and exits in the y direction? No. Here's a case of what I had drawn on the picture here earlier on the board. If you draw your y ray this way, you're on the lower half of the parabola, the upper half of the parabola, so you have to do this. But then notice, as soon as you pass that point of intersection, you've got a different entrance and a different exit. Because your space is just this little surfboard fin right here. So if you committed to doing the y direction first, you've got to do one double integral for this entrance and exit in y direction up until that point. Evaluate that. And then starting from here to here, you have another completely separate double integral set of limits to do. So if you decide to do y first, you're committing to doing 2 double integrals for the whole one thing. Versus doing the x direction first, one double integral gets it all. So,
Shouldn't you have dx?
oh yeah, I mean I usually just sort of say, x then y. But I have actually started doing that for this class for some reason. Putting the differentials there. So x goes from lower to upper. So if I go on the x direction first, no matter which way I draw that horizontal line, I'm always going to enter at x equals the parabola, y squared minus 3. And I'm always going to exit at x equals half y. The equation of the line solved for x. Or 1/2 y or y over 2. Okay? Now when this is flattened to the y-axis, do you know what your y limits are going to be?
Negative square root of 3, this is square root of 3.
No, it's negative
It's
3.
negative 1.5 and 2.
I don't think so. I gotta find out where these two things meet. So,
Oh, yeah.
this solve for x is y squared minus 3. This solve for x is y over 2. So you set the two equations equal to each other. Oh, I think you're right. You are going to get a half value as one of your intercepts. Okay. Sorry, I totally doubted you. You're such an ass. Okay. 2y squared minus y minus 6. Lo and behold, Kai, it's that AC method again, or bottom to top method.
Yeah.
Or quadratic formula, whichever your poison du jour is. To get a negative 1 in the middle, I'm going to want 2 and 3 with minus there and plus there. Yep, Nicholas, I never will doubt you again. Negative 3/2 is that lower y limit. Positive 2 is that upper y limit. Because when this is flattened to the y-axis, that smushes to here, this smushes to here, and that one-dimensional interval, would be your outer limits for y. just solving that equation. That's why I eliminated x. Since I knew I wanted y values from the y-axis, solve the equation for the y values. I don't really need the x points of intersection. So, you got a fraction in this. You got two fractions in your limits. No big deal. That's not a problem. The integral's not too terribly bad. You're integrating the function xy. So, and keep in mind, if you choose to do the y order first, you're committing to two different double integrals. Let me pause for a second and see if you have any questions. Keep in mind, it's open forum. It's not a bad idea to have questions because, heck, this is a contact hour with your teacher. I'm pretty good at this stuff. So if I commit to doing, I have committed to doing x first, our integrand is just xy, so that'll become half x squared, y is a floating multiplication constant there. I'm plugging y over 2 in first, so watch out for your meticulous algebra you got to deal with. 1/2 y times half y squared, and then minus 1/2 y times y squared minus 3 quantity squared. I'm not sure why I had those outer parentheses there because they're completely useless. That's going to give me 1/8 y to the third from this guy right here. That requires foiling. So let me kind of marginally FOIL this out to y to the fourth minus 6y squared plus 9, and then distribute this negative half y through that. You got a little algebra. Minus 1/2 y to the fifth plus 3y to the third minus 9/2 y. Double check my arithmetic. That FOIL correctly. That times that, negative half y to the fifth. That times that, positive 3y cubed, yay, minus 9/2 y. Okay. And only a couple of like terms. Those two. So I'm in my next step integrating negative half y to the fifth, 1/8 and 24/8 is 25/8 y cubed, and then minus 9/2 y. And then, okay? When I get in integration land, I may go off to myself, but if I lose you along the way, just raise your hand and I'll reduce my fervor. Okay. So integrate with respect to y. I can count 2 now. That's going to give me negative 1/12 y to the sixth plus 5/4, so that's 25/32 y to the fourth, and then minus 9/4 y squared. Ooh. So, let's do this. Let me show you a cool trick on the calculator that may save you some time if you have funky limits to plug in. What's the matter? Everything okay? Everything all right? Okay. One thing you can do is obviously, oh no, my calculator's going to die. So one thing you can do is obviously store values as the variable and plug in your antiderivative. Let me show you something you can do with the y1, not the graphing screen. I'm not using it for a graph. I'm using it for something else. If I type in a function for y1, and ideally for this purpose I'm going to type in my antiderivative. Of course I have to use the variable x, but it's not a big shift. So negative 1/12 x raised to the sixth plus 25.
You gotta take that out of
Oh, poo! I keep forgetting I got a new operating system. Okay, good deal. Negative 1/12 x to the sixth, and that is in the numerator. It knows its order of operations, I promise. And then plus, thanks for reminding me of that, 25/32 times x raised to the fourth, scoot out of the exponent, minus 9/4 times y squared, or x squared. Okay, one thing you can do, some of you may know this, some of you may not, so I appreciate your patience while I enlighten everyone. You can actually pull this function up on the home screen and do inputs and outputs with it. Let me show you. And by home screen, I'm talking about this screen right here, your main screen where you do most of your calculations on. What you have to do is you have to go to the VARS, the VARS menu. How many of you ever used that menu before? Okay, because it gives you access to all the variables you have on the calculator. The variables that define the window, the Y1 variables, the letters, the anything, the matrices, anything you can store as a variable. If you hit the vars menu, notice it pulls up just another vars menu here that deals with different aspects of graphing and tables and stuff like that. What you want to do is cursor over to Y vars. If you cursor over to the Y vars, and this looks kind of contrived, like a big old hot mess, but I promise you it's really kind of handy when you have funky numbers to plug in. When you pull up Y bars, it pulls up the different things your graphing calculator can produce on the Y1 or the Y equals menu. You can graph functions, you can graph parametric curves or polar curves. Surprised it doesn't have sequence here, but it doesn't. But you want to access function because you typed it in as a function in function mode. So vars, Y vars, select one for functions, and then pull up Y1. I want to access the function I've got currently stored in Y1 on my Y equals screen and use it on the home screen. And here's the way you do it. Pull it up, and if I wanted to take a function and evaluate it 2, I mean, this is the symbolic version of evaluating a function with an input of 2. This function is named Y1 for the calculator. So what I do on the home screen is I take Y1 and then next to it in parentheses, just like you're doing a function input and output, tell it what you want to plug in. I think I do want to plug in a 2 because the top limit for my antiderivative is 2. So if I do that, the calculator recognizes this as, okay, I'm going to the function named Y1, I'm going to plug in a value of x equals 2, and then I'm anticipating the need for a fraction, so I'm going to frac it on the end. So if you go to that antiderivative and you plug in negative, or you plug in 2, you get an output of negative 11 over 6. Even better, hold up. Since my ultimate goal was to plug in 2 and then separately subtract what you get when you plug in negative 1.5,
all you have to do is
you could do it in 2 steps. Or in the same step. You can go Y bars, function, Y1, evaluated at 2, minus, you gotta do it again though. For every access of Y1, you gotta go through that whole subroutine. Vars, Y bars, function, Y1, evaluated at negative 1.5. And then again, if you can tag it with a fraction if you're anticipating a rational number. But that way, it does the same thing. Inputs 2 into your antiderivative, subtracts an input of negative 1.5 in your antiderivative. It'll turn into a rational number if it is rational. And yeah, so 343 over 1536 should be the value of that double integral. Okay? And so let me see if that makes feasible sense. Because something that's lost on my generation and your generation is, well, seeing if that is reasonable based on the semantics of the problem. You know, the few generations before us that use the slide rule, you ever heard of the slide rule?
Mm-hmm.
Yeah. They kind of had to develop a whole routine of saying, well, this answer seems reasonable based on these calculations that I've done, with the slide rule. My generation, your generation, you've been taught to just data enter, data enter, data enter, enter. And then, I trust this completely, no matter what it is, okay? Just double check your answer and see if it makes reasonable sense. This function is going to have what kind of outputs on this region? Pretty ones? No. I'm thinking of, look at the individual quadrants. Right here, you're in the first quadrant, where x and y are both positive. So the outputs for this function, x times y, should be entirely positive. Okay, so I should have the function being up above the xy plane on that space. That should represent a positive volume. For this chunk right here, which appears to me to be the biggest chunk on the domain, you have negative x's times positive y's in this region, which should generate negative outputs. And then down here in the third quadrant, you have negative x's and negative y's multiplied together. So your outputs there should also be positive. So according to this, that's almost 0.2-ish, something close to it, all right? So apparently, you still have enough positive outputs to, I guess, take care of all these negative outputs you have. So maybe that's seemingly reasonable. Did anybody get something different? Or did y'all all do it the same way I did? Do the whole Y1 trick? You did something different?
Yeah, but I got something that's like super duper wrong. It's a negative answer.
Oh, so you did get a negative answer.
Yeah.
The only thing I can imagine is, garbage in equals garbage out. my antiderivative is supposed to be negative 1/12 y to the 6th. So, okay, that checks out. Plus 25 over 32 y to the 4th minus 9/4 y squared. I did the inputs and outputs correct. The only other thing I can imagine is screwing up something else.
Yeah, I think I just.
Oh, did you? I mean, I make
I did
mistakes.
something
You'll see me
like,
make mistakes.
Totally different.
That's why I was kind of apprehensive about this being a positive answer when I got to my final answer.
It's because you have negative 11 over 6 and then minus 1,053 over.
Oh, for the
500.
individual numbers?
Yeah.
Oh, okay.
Individual numbers and then.
But still, you're using the calculator. I mean, and I'm not sloughing off on using the calculator. I mean, it's a handy thing. But I want to double check, if this makes reasonable sense. And I'm kind of questioning it because negative outputs were the biggest chunk here in the second quadrant, positive outputs here and here. And you think that seems to be the biggest part, but, well, no. Actually, if you rotate that around, that would be bigger than the difference there. So maybe you do have more positive outputs. Well, you obviously do have more positive outputs than negative outputs. So, okay, I'm not so bad now. I'm better. I like that. I'm circling this because I believe it to be correct. All right?
So then in this case, this one just gives us the difference between our negative and positive. This would not be a volume.
No, because there's no volume tie in here because you have different sign outputs. And so since you get a positive answer, that just means you have more positive outputs generated from that part of the domain than you have negative outputs generated from that chunk. So it's kind of a net result. Yeah. And that's okay. It doesn't always have to be a volume problem. But I always want to double check because, I want to make sure my answer seems to make sense or, makes reasonable sense. And try to develop that skill set, not just in math class, but in your physics classes, your ENS. Well, you're probably all past ENS, but just see if your answer kind of makes sense. That's an area problem, but I got negative 32. Well, they're wrong. Area should be a positive 1. Yes, sir.
Where do I go to enter the negative 1 over 12 y to the 6th?
Oh, what I did, you were on your own little world.
Yeah,
You go to the y equals screen, and sorry for the glare. But enter your entire antiderivative there as
With the
y1,
x, okay.
as
Yeah,
though you
okay.
were going to graph it, but you don't have to graph it.
Yeah. I thought you'd gone in somewhere to enter it as a y
No,
variable.
no, you can pull up and
Okay,
store it
thanks.
in different places, but that's the most practical place to store your y1. And then go to the vars menu, vars, cursor over the y bars and
I
function,
got all that.
and then that allows you to pull it up on the home screen and do calculations with it, with function input and output. It's kind of handy. How many of you didn't know that? Yes. All right. Cool. Taught you something cool. Yes, sir.
If we wanted to do the volume, we'd have to do 3 separate double integrals?
If you
and add them
wanted,
all together?
yeah, if you realize that someone mentioned the context of absolute value earlier. Yeah, if you did want to think of what's the total positive volume up above the xy plane and what's the total negative volume below, you'd have to do it as 3 separate double integrals over those separate regions. But you'd also want to look at the function, and some functions are harder than others to do this with, is to see, well, where are my positive outputs going to be? The function here is just simply x times y. So if both have the same sign, negative, negative, positive, positive, you have positive outputs. If they have differing signs, like in quadrant 2 there, you'll have negative outputs. So sometimes it's harder to isolate where those positive and negative outputs occur. But yeah, if you wanted the net negative and the net positive all together as absolute value, you'd have to commit to 3 different double integrals. Yeah. Because just like in Calc 2, it's impossible to integrate a function that has absolute value bars on it. If you have absolute value in your function, you have to break it up into here's the negative output region, here's the positive output region, and then take the absolute value of each individual regions. Enter. Last one. Changing the order of integration. And I did this, we did this as our first example just to make sure you're realizing the versatility of integration. There's a handful of problems that I've got deliberately put on this homework that are completely impossible to integrate in the original order of integration. But